Hello everyone, my name is Rosemary Namenya and today I'll be presenting to you my final recurring neural network for sequence data project. The project overview is as follows. It starts with an overview of a time series dataset that is in part 1, followed by simple RNN with sine wave data, part 2, then part 3 is a discussion on the LSTM neural network, part 4 is building an LSTM with time series data, then redesigning the same with different parameters in part 5. Part 6 explains the comparison of both models in part 4 and 5. Then I conclude with the conclusions. Part 1 shows a time series dataset. The name of the dataset is monthly beer production in Australia. The data type is a univariate time series dataset, meaning it has only one variable, and this is the snapshot of the dataset. As you can see, we can only see one variable here, and it's the monthly beer production. The total observations in this dataset is 476. The time span is between January 1956 to August 1995. The data was obtained from Kaggle, and this is the link where you can actually download the data. So part 2 of the project required generating a simple RNN with sine wave data. But before I begin showing you the coding steps that I undertook, I will first begin by introducing what a simple RNN is. So it's sometimes called a vanilla recurrent neural network, or an Elman RNN, which was named after Professor Jeffrey Elman. The state consists of only one hidden vector H. It is just a single layer neural network with feedback. So actually this is the feedback over here. This is the diagram of the architecture of the neural network with two layers for the model. So we have the simple RNN and the feed-forward neural network. This is subnetwork 1, this is subnetwork 2. These are the previous states, these are the current inputs, these are the biases, these are the output layers, these are also the output layers, then these ones are actually the hidden layers. In this step, I will show you the coding steps that I undertook in Python to build, train, and test a recurring neural network using the sine wave data with simple RNN keras. So first, I started off by importing the basic libraries, that is the pandas, the numpy, and the matplotlib, which is used for data visualization in this case. So the next step was importing the model, which was the sequential model, and then the layers, that is the dense and simple RNN. Then the third step was importing the time series generator and the min-max scaler. So the min-max scaler is used for data normalization, and the time series generator is used to generate the batches that will be fit in the model. So what followed next was data preparation, and that was generating the data, and the data points that I used was 0, 70, and 1006. So the range of the sine wave is between -1 and 1 for y, and for x is between 0 and 70. So this is actually like just the visualization of the data. So in this step, I uploaded both X and Y. So I defined the length in the data frame, which was 1006. I split the data set into two parts, that is training and one for testing. So the testing was 20% in this case, which was 201.20. And this is just like displaying the 10 fast view values of the data set. So this is a continuation of the process that I undertook. So here we can see the last 160 values of the original data set for the test data, which is 201. Then this is the index for the first data point. And then here we just see like a display of the trained data, the first 10 values. And here we can see the signed values as well. So in this step, I normalized the data using the min-max scaler, and then I used 48 historical points to predict the next one. So that is what I set here. And then the batch size was 1. The next step was building the simple RNN model. I specified the features 1. The model is sequential. And then we can see the neurons that I used here and defined was 99. And then the dense was 1. 48 historical data. So this is what I'm going to use to predict the next value. So to compile the model, I used Adam as the optimizer, which is one of the best. And then for the loss, I used the mean squared error. And then this is the model summary. We can just see here, it gives us the output of the shape, the parameters, and the layer type. The model, as it indicates here, is sequential. So we have simple RNN and a fully connected layer, which is the dense. So total parameters are 10,099. So in this step, I trained fit the model, and I used the model fit generator to do that. And then the model will be trained using 6 epochs. This was like the visual after the whole entire process, and we can see like a significant drop over here, a slight rise, then some bit of steadiness over here, a slight decline, then a bit of steadiness on this other end. So in the next step was evaluation model on the test data. The length was 48, and then we had the 48 data points displayed. This is like just like a snapshot, but then we realize here that the shape is 2D and it must be 3D. The shape is 2D because you can count the box brackets here and there too. That indicates that the shape is 2D. So it's therefore necessary to reshape it. To reshape it into 3D, this is the code that I used over here, and this is the snapshot of the results to confirm the shape. This is the code that I used to confirm the shape, and now we can see that the shape is 3D because when you count the box brackets over here, there are 3, which is now good. So in this step, I show you like in the overview of the data set with one attribute, that is the sign values. So it's 200 rows by 1. So I'll use this code like to show you the overview of the data set with both the 2 attributes, that is the sign and the prediction values. So here we see the results of the 2 attributes presented here. This is like just a snapshot. So we can see here it's 201 by 2. So we have both the attributes over here combined together in one table. So the sign are the actual values, which are the real values, and then these are the predicted values. This is the visualization of the model evaluation results, and as you can see over here, the lines are very close initially when it starts, which shows the accuracy over here is very good because the prediction values are very close to the actual values. But when it start moving, we can observe a few gaps over here, over here, as it just picks the pattern. The pattern is pretty much similar, which is a good thing. The accuracy here was good here. The accuracy started like dropping. So, but we can say it's not a very bad prediction. The accuracy is not very bad considering we used a very simple type of RNN. So in this part 3, we discussed the LSTM neural network, and I start by discussing the vanishing gradient problem, which is a common problem in simple RNN networks. So yeah, so the vanishing gradient occurs when the gradient becomes very small, as we can see over here. This is because it occurs as the back propagation method moves downwards from the output layer towards the input layer. So the gradients frequently grow smaller and smaller until they finally approach 0. Leaving the weights of the initial or lower layers is essentially unchanged. Because of this, the gradient descent never reaches the optimum. So this is just like a screenshot showing you like the back propagation method. You can see here where the actual layer the gradients become smaller and smaller. So some of the solutions to the vanishing gradient problem are using the ReLU function, the leaky ReLU function, and the weight initialization. So in the ReLU function, it is used to activate the neural network instead of a sigmoid function. The partial derivative of the loss has values of 0 or 1, preventing the gradient from vanishing. And then the leaky Rayleigh function comes in play when when we need to stop the gradient from decreasing to zero, because the Rayleigh function becomes problematic when that problem occurs. So by using the leaky Rayleigh function, it stops the gradient from decreasing to zero and the problem is avoided. The next method for avoiding the vanishing gradient problem is using the weight initialization, which is a technique of settling initial values to the weights in the neural network so that the weights never vanish during backpropagation. So the next part, I discussed the exploding gradient problem, which occurs when the gradient becomes very large, as illustrated in this diagram. So the problem occurs when some gradients continue to grow in size as the backpropagation technique advances. So as you can see over here, the gradients are increasing in size as opposed to the vanishing gradient problem that I actually showed you in the previous slide. So as a result, very large weight updates occur, causing the gradient descent to diverge. Some of the solutions to the exploding gradient problem include redesigning the model with fewer layers. Here you just reduce the number of layers in your model. Then the second one is using weight regularization by imposing a penalty to the network's loss function for large weight values. And the third one is using gradient clipping. This is where the gradients are clipped during backpropagation so that they never exceed some threshold. And then the fourth one and the final one is using long short-term memory networks, the LSTM. So they usually handle the problem using an original additive gradient structure that includes direct access to the forget-get activations. So some of the limitations of the simple RNN are actually the vanishing gradients, and that is what they really suffer from. So the vanishing gradients and also the exploding gradients, and it's actually what we have just discussed in the previous slides. So this is what RNNs actually suffer from. So LSTM neural network are actually the solution to the limitation of a simple RNN. As I have just discussed in the previous slide, we have seen that RNNs actually suffer from gradient problems. So the LSTM has an internal state of their memory that allows gradient to travel through many time steps without vanishing or exploding. It also helps to achieve uninterrupted gradient flow as shown in this diagram over here, and also it has the forget gates which keep some information from the previous cell C state, thus preventing the vanishing gradient problem. Therefore, in general, LSTM is known to be a very powerful solution to the gradient problems and mostly the vanishing gradient problem. So now in this step, I'll discuss part 4, and that is the RNN, LSTM with time series data. And here, before I begin the coding steps, I will show you the LSTM architecture that will be used. So it's going to have 3 LSTM layers, and this is the architecture. So we can see here we have 1, 2, 3 LSTM layers, and it's going to have 2 dropouts, so we can see over here, and 1 dense layer. So this just shows like an overview of the architecture. So in this step, I will discuss the summary of core parameters that I used, and the percentage of data for testing. I used 0.2. I used 3 LSTM layers. I used 42 neurons per LSTM layer, and dropout layers were 2. The percentage to drop out layers was 0.4, and then the time series input sequence was 55. The batch size for training was 25. The batch size for testing and forecasting was 1, and the number of epochs for training was 48. So in this step, I will take you through the coding steps in Python that I undertook to build, train, test, and forecast the LSTM with time series data. So I started by importing the basic libraries, and this is the pandas, the numpy, the matplotlib that are used for visualization. Then next, I imported the models from TensorFlow, and also related to Keras. This was the sequential model. Then for the layers, I imported LSTM, dropout, and then the dense layer. Then I also imported the time series generator and the min-max scaler for the same purpose that I discussed earlier for the sine wave data. And then also, the data set was Walmart stock that I got from Yahoo Finances, and this was the date range, 1st October 2019 to 29th July 2022. So this was the file that I actually downloaded from Yahoo and uploaded into the Jupyter Notebook folder. And then the next step, I actually just displayed the data set, the first 5 values, and we can see actually the snapshot over here, and these are the various attributes. So in this step, I explore the data analysis. This is just defining the shape. We have 895 observations, and also this just the data types. For example, this is an integer. So this then I explored the summary statistics, and this just shows like a snapshot of the summary statistics. So we have like the mean, the standard deviation, etc. So the next step was filtering out all other attributes and remaining with closed value only, because as per the project requirement, we actually had to only deal with one attribute, and I had to perform pre-processing to achieve this. So these are the steps that I took. These are the codes that I used. So just to display like the first 5 values of the closed attribute, I use this code, and these are the values. Then to visualize the closed attribute, I use this code, and this actually shows the visual of the closed attribute that we're gonna focus on in this project. Next, I define the length of the input series using similar codes like the ones I discussed earlier in simple RNN part 2. So in this case, I used 55 historical data points, and then I set 2% on test data, then split the train and test data. I display the values to visualize the first 5 data values. Next, I normalize the data using min-max scalar, just similar to the way I did in part 2. So I haven't shown that here, because it's actually similar to the other one that I did in part 2. And then next, I created the time series generator as shown in this slide here, over here, and also the length, define the length of the normalized train data. So we have 716. Then we can see the batch size here is 25, the length is 55, and then actually just printed both X and Y to just see how the first batch looks like. So the next step, I build the LSTM model, define the features as one, and then the model was sequential. Please ignore this. And then we had 42 neurons, and then the length was set to 55. Then I added one dropout layer, 0.4%, and then I added the second LSTM layer. And these are actually, as you can see over here, I added another dropout layer, and then I added the third LSTM layer. And then finally, I added a fully connected layer for the final prediction, then compiled the model, and these are the results. So basically, it shows us we have 1, 2, 3 LSTM layers, we have 2 dropouts and dense. These are the parameters, and then this is the output shape for the whole model. So then I visualize the model's performance after training. You can see I used 48 epochs, and then this is the loss data. We can see a significant drop here, and then this pattern is what follows: slight decrease, slight increase, like that, some constancy, and that's what follows, what we can visualize from the plot. And then next, prediction for testing, I used the time series generator. Batch size was 1. Then to view the normalized prediction, I used this code. So the next step that followed was to get the length of the normalized prediction, converting normalized predictions back to true values, flattening the 2D array, and then I visualized the predictions. And in this step, I visualized prediction by combining it with close price in the same plot. So that step I haven't shown in here because it's pretty much like the same concept that I used for the simple RNN. And then so in this screenshot, we can see the visualization plots for the model performance after training, and we can see the orange lines here, which are the prediction, and these are the closed values. So there's actually a gap over here, and the pattern that predicted the values is actually almost similar. We can see it picked it kind of picked almost the similar, but the problem is there's a gap here, so it shows the accuracy is not good, and because it's not close to the actual values, right? So the pattern that predicted value is actually similar here, so that's actually a good thing in terms of the pattern, but the model accuracy was not good. So the next step, I created a time series generator for forecasting. I specified the length still at 55, then created the time series generator for forecasting, and this here is the code that I used. The length I specified for at 55, batch size still 25. Then next step was building, compiling, and fitting the LSTM model for forecasting. The number of epochs I used was 48. And then to forecast, I set the periods of the time span for forecasting. In this case, I forecasted for the next 49 business days, and this is the data range from 30th July 2022 to 9th October 2022. So the first Evil batch, this is actually just shows you the code that I used, and then also these are the other codes that I use to update batch to include prediction and drop fast value. So in this tab, I created a new timestamp index with pandas for the time range that I just talked about in the previous slide, and then set the codes as shown in the slide, and then plotted the forecasts for the close values. This is the visual, this is the pattern that it takes, and then the forecast, this is the pattern that it takes. So the next step, I uploaded the dataset again with the data frame as I had specified between this time period that shows for the next 49 days, and this is the new dataset. And then just visualized the first few values of how it looks, and then I'm still going to just deal with one attribute, and that's the close attribute. So these are the results of the forecast. As you can see here, these are the blue lines are the close values, the forecast is the orange line, and from the results, the model performance did not forecast very accurately at all. The predicted values, which are the orange ones, are far away from the blue values, which are the real values. Their patterns are different from each other. This is explainable because we only use the last 55 data points of the complete data set, but after that, I used the forecast values, which are not the real values. Therefore, with the forecast, the model tries to give us a trend of how it should be. So we come to part 5 of the project, which was to redesign the neural network for the LSTM that I've just done and explained in the previous slides. So I still use the same architecture. I use the 3 LSTM layers, and this is the display. So we have 3 LSTM layers, 2 dropouts, and 1 dense layer. So the summary of core parameters for the redesigned neural network was as shown in this screenshot. The percentage of data for testing was 0.1. I used 3 LSTM layers, 130 neurons per LSTM layer, and number of dropout layer was 2. Dropout layer, the percentage to drop was 0.2. The length of time series input sequence was 30. Batch size for training was 15. Batch size for testing and forecasting was 1. And then the number of epochs for training was 50. So this is the model performance after training and the time series forecasting results. So I haven't shown you the steps I took, like, because they're pretty much the same as the ones I took in the previous one, just with the changes with the core parameters. So these are the results. Model performance after training and time series forecasting. So from the above visualization plot, for the model performance after training, the orange lines are the predicted values and the blue ones are the closed values, which are the real values. So the model did not perform that well. It's not close to the actual values. There is a small gap observed over here, and the pattern that the predicted values picked is somehow like the actual values, but generally yeah, the pattern is actually the same, as you can see. But generally, to conclude, the model's accuracy was not good but better from the previous design. Then from the time series forecasting, the model performance did not perform accurately at all. All the predicted values are far from the real values, as you can observe over here, and even the pattern is very different. However, we note that the model tries to give us a trend of how it should be. So this is just like a comparison of the core parameters that are used in the previous model in part 4 and the redesigned model. So because we want to check for what the differences, right? Like what might have influenced the differences in the results of the performance. So the first model, percentage for data testing was 0.2. The next one I used 0.1. The LSTM layers were the same at 3. The number of neurons in the first one was 42, but increased to 130. The number of dropout layer for the first one was 2. The second one remained at 2. The dropout layer, the percentage to drop, the first time I used 0.4. The next time I used 0.2. The length of time series input sequence, I used 55 for the first one. The next one I used 30. The batch size for training, for the first one I used 25. For the redesigned model I used 15. The batch size for testing and forecasting were both the same at 1. The number of epochs for training, the first one I used 48, and the number of epochs for training for the second redesigned model was 50. So based on the modifications, increasing the number of neurons and epochs were 2 viable parameter improvements that would have enhanced the data. When data is huge, as it was in this situation, since we had a large data collection, increasing the epochs can sometimes assist to increase accuracy. Also, in other cases, decreasing the batch size also sometimes helps to improve their network performance. So when you compare the network performance, I start off by comparing the model performance after training for both models, and this was the first one as we had discussed, and this is the second one. So the orange lines are the predicted values, the blue ones are the closed values, which are the the true values. So the model did not perform that well. It's not close to the actual values. So this is the redesigned model. It's not very close to the actual values. There is a small gap observed. The pattern that the predicted values picked is somehow like the actual values. Like, yeah, just the pattern is the same. But generally, to conclude, the model's accuracy was not good, but it's actually better than the first one, as you can see here. When you just check, there's a notable difference. Like here, it's actually approaching to the closed values, as opposed to here there's a big gap. And then when you check the pattern here, it's actually trying to, it's almost same to the pattern over here as opposed to this one. So there's actually some improvement despite the fact that the model performance is still not considered to perform very accurately. However, the model tries to just give us a trend of what's going on. Yeah, I did a comparison of the time series forecasting results. I already spoke about the interpretation of the results, but now we're just comparing. So this one is for the redesigned model. This one is part one. So the blue lines, as we note, are the closed values. The forecasted lines are the ones in orange. So we can see a slight improvement for sure. There's a slight improvement for sure, but the model is still not considered accurate. But we can see this line, the orange line, has actually tried to move higher as compared to this one. So we can see that it's trying to move to the closed values, but we still see their patterns are very different from each other, and this is explainable because we only use the last 30 data points for the complete data set. But after that, I use the forecast values, which are not the real values. And therefore, with the forecast, the model tries to give us just a trend of how it should be. And same applies to this one. But all in all, overall, we can see there was something like there was a slight improvement. So basically, the key takeaways in this project while dealing with simple RNN and LSTM, I note that simple RNNs are good for sequence data such as language because of their internal memory, but they also suffer from limitations, that is the gradient problems. And then LSTM was developed as a solution to the gradient problems encountered in the simple RNNs. Lastly, when I also noted when you develop neural networks they usually have the ability to learn outside of their training, making it difficult to control how they learn. Improving a model's accuracy can be accomplished by increasing neurons and epochs, reducing the byte size, and so on. However, these parameters do not always enhance performance accuracy in all situations. And just by giving an example, sometimes they can cause overfitting or underfitting. So it's usually they keep changing, and yeah, that is what I have learned. But generally, there's some parameters that actually really help, are especially increasing neurons, working on a large data set, and so on. So this comes to the end of my project presentation, and I hope you actually learned something from it, and I hope you enjoyed. Thank you so much, and if you have any questions, please feel free to reach out to me. Thank you.